what is type 3 superconductivity? In the first few slides of this talk, I will try to give you what I can define the take-home message, the key features of this, what I mean by type 3 superconductivity, and in the rest of the talk, I will try to, without going too much into detail, to show how all these arise. In this talk, I will use a relativistic notation for simplicity, although, as we heard yesterday from the talk of Carlo Trugenberger, the correct formulation of this problem should have been done on the lattice, where an ultraviolet cutoff naturally arises. So what is type 3 superconductivity? Let me start from superconductivity, and I've written there a field theories perspective. What I mean by a field theory perspective, what I mean is that I will not use a microscopic approach, but I will use a long distance effective gauge theory approach to catch the essential features of the problem that I want to study. So let me start with 3 + 1 dimension. If I'm in 3 + 1 dimension, I want to describe superconductivity in this way. I can do this using the word of Weinberg. So a superconductor is simply a material in which electromagnetic gauge invariance is spontaneously broken. If I take this point of view, what I can derive immediately is that I have the screening of the electromagnetic field. I have the Anderson-Higgs mechanism. I can construct a phenomenological model, the Ginzburg-Landau model, to describe superconductivity, and I have the Meissner effect. In 3 + 1 dimension, I want to stress also that Coulomb interaction in this game, they are subdominant. Now, what happens if I change dimension? Let me move to the 2 + 1 dimension. And first of all, let me define what is for me a 2 + 1 dimensional system. So what I will talk about are superconducting films that have a thickness d that is comparable or smaller than the coherence length. Now, if I do this, the first consequence that I have is that the screening length becomes comparable or even bigger of the size of the system. This is an example, for titanium nitrates. And the system that I want to describe are systems that harbor the superconductor to insulator transition. And what is the consequence of this? The consequence of this is that the dielectric constant is huge. And having a huge dielectric constant has the consequences that the electric flux lines are confined on the plane. And so what I have is an effective 2D logarithmic potential, a real two-dimensional Coulomb potential between charges on scale that are between d and this screening length that is epsilon times d. So what I will show you is that in this condition, the Landau-Ginzburg model cannot describe superconductivity. So what fails? Now, Coulomb interactions are important, and so what I have is that if I couple electromagnetism to the Ginzburg-Landau model, what I get is 2 + 1 dimensional scalar QED. Now, this 2 + 1 dimensional QED is a theory that is plugged by infrared divergency. I have the coupling constant, the scale, like the size of the sample, divided by a scale. In this case, I took C. This was shown by Jackiw-Templeton. So what I have is that the system is forced to break in droplets. Droplets that have a size that is comparable with this length scale that I have here. And so what I have is, due to this infrared divergence, my system cannot be homogeneous, but must be granular. And this granularity in film, as Carlo Tugendberger showed yesterday, has been experimentally observed. Now, I have droplets in which I have local superconductivity inside described by this Ginzburg-Landau, but I need a mechanism that will give me global superconductivity, and this global superconductivity will be realized when I can establish a global phase coherence over all these pre-existing droplets of condensate. Now, in this system, what I have is that Cooper pair survive above the critical temperature, and what will cause the destruction of the superconductivity will not be the breaking of the Cooper pair, but will be the proliferation of vortices. This will be Josephson vortices. Carlo Tugendberger introduced yesterday the Josephson vortices. So the transition that I have here will be a Berezinskii-Kosterlitz-Thouless transition. So here is what happened in my films. They break down in droplets. And what I can have channeling between these droplets. And these droplets are characterized by condensate and a phase. And when this phase formed configuration like this, I have what forms is a coreless vortex that is called Josephson vortex. And this is very similar to what happened in Josephson junction array. And in fact, what we have is that the theory that describes this type of superconducting system is the same that describes also Josephson junction array. Now, I told you my system breaks in droplets, and I have to have a mechanism that gives me global superconductivity. To have global superconductivity, I have to have a mechanism that works to screen my electromagnetic field, so I have to have a mechanism of mass generation. And in 2+1 dimension, I have two ways in which I can generate a mass, my screening of the electromagnetic field. The first one is the one we heard yesterday, namely through instantons. And these, we have seen yesterday, give rise to the state of matter that is called superinsulator. And the other one that will be relevant for us is the generation of a mass through a mechanism that is alternative to the Higgs mechanism, and is called the Chern-Simons mechanism, or BF mechanism. BF is not an acronym, it's the name of the theory. So this is a topological mass generation. Now, I thought about 2 dimension, but is this limited to 2 dimension? No, the answer is no, because this mechanism of generation of topological mass can be extended to any dimension. And moreover, it has been experimentally found that granularity is not confined to films, but can exist also in bulk sample, and it has been found also on the ground state of ITC superconductor. And what I will show you is that, in fact, what we can have is a generalization of the Beckett-3 transition to any dimension, and in particular, in 3 dimensions, this Beckett-3 transition will become what is called the Vogel-Fulcher-Tamman transition. So what I said for film in 2 dimensions can be extended to any dimension, in particular to 3+1 dimension. Now, okay, this is the take-home message. Now let's see into a little bit more detail, how this mechanism of mass generation that is crucial to obtain the screening of the gauge field works. Now, let's start from 2+1 dimension, and let's consider the usual Maxwell action, F mu nu, F mu nu. We all know that we can give mass to this gauge field through the Higgs mechanism. I can add this term with the covariant derivative, and I have 2 possibilities. I have an unbroken vacuum in which I have a complex scalar field that has two real massive degrees of freedom and one massless gauge excitation. Now, if I go into the broken vacuum, my gauge field becomes massive, and so I have 2 degrees of freedom for that, and I have a massive chargeless Higgs boson. This theory respects the P at T asymmetry, parity at time reversal, and this is the phenomenological theory that I was discussed before for what is called, let me call it standard superconductivity. Is this the only way? No. Deser-Jackiw-Templeton show us that you can, instead of adding this term, you can add a term. Here you have the gauge field. So you see you have a new term that is a term that is quadratic in the gauge field, but contain only one derivative. So it's a term that is dominant at large distances, and in which the index are contracted with the totally antisymmetric tensor. If I add these two and I compute the equation of motion, what I see is that a mass appears. Remember that in 2 dimensions, this object has the dimension of a mass. So a mass term appears, and I have that my theory describes a single degrees of freedom that has a mass. My gauge symmetry is not broken. And if I will compute the Gauss law, I will see that this term has the peculiarity of connecting electric and magnetic fields. So magnetic fields are as a source for the electric field and vice versa. And if you look at this theory now, what you have is that this theory breaks P and T symmetry. And so this theory combined together was used as a phenomenological theory to describe, for example, the quantum Hall effect, or was used for what was called anion superconductivity, when it was believed that anion superconductivity was a T-breaking theory. Now, let me just stress another characteristic of this term. If you take this term by itself, it doesn't describe any dynamics. Its Hamiltonian will be 0. It describes invariance of curves and oops, sorry. Okay, so it's a term that so this Chern-Simons term, pure Chern-Simons term, is a term that do not describe any dynamics. And so, as we will see, when we use it in physics, we should add other terms that introduce the dynamic for us. So my films, the system I start with, is a system that doesn't break P at T. So can I use this topological mechanism by having P at T symmetry? Yes, I can use this topological mechanism. And the way I can use this topological mechanism is if I write this Chern-Simons term, now here I write it in Euclidean spacetime, if I couple a vector and a pseudo-vector field. If I do this, and then I will check the P and T symmetry, this theory respects P and T symmetry. And this is what is called the mixed Chern-Simons theory, or BF theory. Now, again, I should add the kinetic term for the gauge field A and the gauge field B. These are these two terms here. And I will have the analog of what I had for the Chern-Simons, pure Chern-Simons theory in terms of two gauge field. Now, as I told you, we want not to be confined to 2 dimensions. So let's see if I have a way to generalize this term to higher dimension. And the way it exists in 4 dimension, 4 Euclidean dimension, epsilon has 4 index. So if I want to have one derivative only, I need to have an object that can saturate 3 index. So what I do is I take a vector field and I couple with a pseudo-tensor field. And this is what is the BF theory. And this is the generalization with the kinetic term add. This is just the equivalent of the Maxwell term for tensor field. And this is, again, the Maxwell term for the A field. This action was originally, in 2 and 3 dimensions, was proposed by us, Pasquale Sodano, Carlo Truggenberger, and myself, back in 1996 to describe topological phases of matter. Now, what are the characteristics of the Chern-Simons and the BF action that I wrote is that, again, the two emergent gauge field, or the gauge field and the pseudo-tensor gauge field, acquire a mass that is given by this expression. The coupling of the Chern-Simons term is always taken dimensionless. And now if you would look here to the coupling constant that you have, you will see that they have the dimension of the mass. In 2 dimensions, they are naively irrelevant, and in 3 dimensions, this one is marginal, while the other one is still irrelevant. And so what you will think is that this, if I go back, so these 2 terms will not influence the phase diagram. This is not true. And this is due to a peculiarity of this Chern-Simons term, and from the fact that if you want to correctly define the pure Chern-Simons limit in which the topological mass goes to infinity, you see that these terms are necessary because the quantization of the theory will not commute with this limit. So these terms are relevant, they play a crucial role, especially what plays a crucial role is the ratio, the dimensional ratio between these 2 coupling constants, as we will see. Now, where this theory, I wrote down this topologically massive theory, and now I would like to see what is the connection of this theory with my system. I say that I want to describe a system that have the superconductor to insulator transition. So let me try to see how can I describe a theory, an effective theory for this system. I know that in this system, the relevant degrees of freedom are Cooper pair vortices. This has been told us by Fisher. And what I know is that I have these 2 quantities that both in the film interacts logarithmically. So I have competition between these 2 quantum orders. And what I have is that these Cooper pair vortices interact through they have a topological interaction, and that is the Aharonov-Bohm-Kasher interaction when you have the word line of a charge that wraps around the word line of a vortex. So what is this topological interaction is the interaction that is dominant at large distances. And if I want to write it, this is the linking number of these 2 curves. This is written in this way. Now, this is non-local, but Wilczek has shown that we can write this interaction local at the price of introducing 2 emergent gauge fields. So I have my theory for the SIT that is dominated by the Aharonov-Bohm-Kasher topological interaction, and I arrive at the local formulation in terms of the 2 emergent gauge fields. In which one is a vector because coupled to charges, and the other one is a pseudo-vector because coupled to vortices. Now, this is not the end of the story because, as we said before, this term does describe any dynamics. If I want to, so I need to introduce the dynamics. If one wants to be really precise, one should say that this term needs a regularization because it has a 0 mode, but we need to add the dynamic. So if I add the dynamic, the next term with the minimum number of derivative and that respect gauge invariance that I can add is this term here. So as you see, I obtain the action that I had before, in which F mu describe fluctuation of charges, is a charge current fluctuation, and G mu is the dual quantity in terms of vortices. Now, here I wrote the coupling constant SEV and AQ because now I'm describing films that have a seat, and I can relate this parameter to the energy scale of the droplets and to the magnetic scale of the droplets. And I can trade these two parameters for a massive parameter, my topological mass, and the ratio that I was telling you about before between these two parameters. And this ratio is the ratio between the electric and magnetic interaction. And when one dominates or the other one dominates, I will get the different phases. Now, to obtain the phase structure, I will have to couple this with the real electromagnetic field and compute the induced action. But just before doing this, let me see, this will be the analog of what I have done in the case of the 3-dimension, with the only difference that now what was the current of vortex that had just one index become an object with two indices, because in 3 + 1 dimension, vortex are one-dimensional objects and describe a world surface. Okay, so if I compute the effective action, this is the phase diagram that I obtain with the parameter eta that naturally appear in our description, and this is G. So you see when G is bigger than 1, I have the phase in which the charge dominate. This is the phase in which vortex, the contrary, vortex dominate, charge dominate. So I have vortex condensate, magnetic monopole condensate, and charge condensate. And in the middle, I have a phase that can appear. You heard everything about this phase yesterday. Let me just stress that this phase in between that appear when this parameter eta is bigger than 1, it's a phase in which this topological interaction that is being ignored plays a crucial role and screen both charges and vortex interaction, and these are both gapped interaction. Okay, 5 minutes. Okay, so let's concentrate on this phase, Higgs-less superconductor. What is an Higgs-less superconductor? This was introduced originally by Pasquale Sodano, Carlo Turgenberger, and myself in 2006, and studied again in 2017. So what I have, if I look at the effective action, the term, the vortex-vortex interaction in the effective action that I was telling you before, normally this interaction is screened by the topological interaction. So here, sorry, the minus sign should be here. So I have the screening of the vortex interaction, and now since I'm in the charge condensation phase, if I look to what happened to this term in the charge condensation phase, I see that the screening is suppressed. The fact that the screening is suppressed and that they interact with the inverse of with the Coulomb potential means that leads to a logarithmic confinement of vortex. And if I do the same thing for the 3-dimension in which I have world surfaces of vortices, again, I see that normally they are screened by the topological interaction, but the charge condensation, again, suppress the screening. So again, if I will look at the analog of the Topf loop for surfaces, I will see again that these vortex are logarithmic confined. So the phase in this Higgs-less phase, Higgs-less superconducting phase is characterized by logarithmic confinement of vortices in 2 and 3 dimensions. And the transition is given by vortex liberation. Now, let me see what is this effective action in this case. Now, I know that vortex are confined, are dilute, so I can write down my action. And this is the action that I obtain. This is the the field that is connected to the charges when I solve the constraint. And this is the real electromagnetic field. So you see that I have a Maxwell term for this term, for the charge here, a Maxwell term for the real electromagnetic field, and these are coupled by a Chern-Simons term. So again, I found that topological mass generation for my electromagnetic field, and I have a screening length that is given by this expression. And the transition is given, as I told you, by the proliferation of vortices. In 2 dimensions, I have a BKT transition, that, so the liberation of vortices, and the scaling that I will have for the resistance is given by this expression. If I will play the same game in 3+1 dimension, what will be the analog is the vortex as a string, the string as a tension. So what will be the analog of this transition will be the fact that this string becomes tensionless. And the scaling of the resistance in this case has been computed in collaboration with Luca Gammaitoni, Carlo Truggenberger, and Valery Vinokur. This is the scaling that you get, and this has the same form as the Vogel-Fulcher-Tamman transition. So this is the new scaling that we have. And this scaling has been observed experimentally by the group in Taiwan. So here is the experiment done on niobium nitrate of 20 nanometers of thickness with coherence length of 4.2 nanometer. And this is a similar experiment done on a thicker sample on niobium titanium nitrate with the thickness of 10 nanometer, coherence length of 10 nanometer. As you can see, we have plotted in blue, in red, the scaling with BKT scaling, and in blue, the Vogel-Fulcher-Tamman scaling, the same here. You can see that, so blue is the Vogel-Fulcher-Tamman and red is the BKT. What you can see here clearly is that the more the system becomes thicker and three-dimensional, the more the Vogel-Fulcher-Tamman scaling better describes the experimental results. And thank you for your attention.
Cristina, thank you so much. And we have time for a couple of questions.
Just trying to understand how different from the XY model your theory is. So in 2+1, for example, if you would integrate out the vortices and just look at the theory for the charges,
okay.
How different would that be from the standard XY model that we all know?
The theory, our theory is completely different from an XY model. You see it clearly here. It's a theory, okay, in which the crucial point is the topological interaction, Aharonov-Bohm interaction between charges and vortices. Okay, so this theory is not an XY model. Now, you say you want to integrate the charge?
That's right. What's left?
Okay, so if you integrate the...
Not the charge, but the vortices, for example. So theory for the charges would be XY model ordinarily, but okay, what is yours?
You will get a theory if you integrate... You want to be in which phase? Sorry, in the phase in which you have a condensate of vortices?
Yeah, whatever.
Okay, in the phase in which you have the condensate of vortices, you will start with the theory, okay, in which you have a condensation of vortices. You will have that these vortices, okay, as Carlo Truggenberger showed yesterday, liberated in this phase, you have the liberation of the instanton that are in a plasma phase. And so what you will get is a linear potential for charges.
Well, I understand that. I understand the description of phases. Mm-hmm. But my question still is, just if you integrate one of these two fields, either vortices or charges, what's left would be some interacting theory for whatever is the left degree of freedom.
This is, okay, when you are in the phase, you start with the theory like this for vortices, okay? You are in the phase in which you have the charge condensation. You have this theory for vortices, you have the charge condensation, and you get this theory for charges.
Maybe I can answer that question directly. If you integrate out one gauge field, in one case you get the pro-Lagrangian, in the other case you get Polyakov's compacuity. This is quite different from the XY model.
No, I agree it is different. My question is exactly that. What is the difference?
I just told you. In one case you get the pro-Lagrangian, in one other case you get Polyakov's compacuity.
Okay.
Maybe I didn't show it very well. I didn't brought this formula, but in this case, as I told you, here you generate a linear potential, so you have a confinement. In this other phase, you do not have a linear confinement. You have in 2 and 3 dimensions, you have a logarithmic confinement, and if you go a little bit beyond this, you can use what is called, you can promote these forms to a 2-dimensional tensor field, and you derive what is said.
I got it. So the transition would be first order, presumably, between these two phases.
Right? This transition here, this is a first order transition. You have is a first order, but these two here are in 2 dimensions. They are BKT transition, even at 0 temperature, and they are Vogel-Fulcher-Tamman transition in 3 dimensions. So the key point is that you have to have these vortices and charges. And if you take the XY model, you would take only vortices.
That's right. That's right. Yeah. Thank you.
Okay. One quick question, if any. Ali, please.
Very lastly, related to what you said, just a curiosity, I say, okay? Just a curiosity, maybe you can answer too. We used to work on YVCO a long time ago, and the oxygen content is very important. Then it becomes antiferromagnetic or superconductor at a critical point for something, oxygen content. What if we were able to make a monolayer or 2-dimensional 1-layer YVCO? And how could you correlate this work to this possible experimental study?
So you want to have a layer of
YVCO with the controlled oxygen content.
By
One
layer,
elementary cell, you mean?
Yes.
So 2 layers. 2 planes.
Yes, 2 layers, yes.
But 2 planes.
Two unit cells on the top of layers. So let's assume like that. Yes.
So you have 2
unit cells.
2 units. Okay. This is what Carlo was explaining yesterday. This okay.
Oh.
Here.
How did you steal my idea? I know.
Oh, it's okay.
So the point here is that system for us will be 3D, because you have 2 layers. So I consider it as 3D. And in this theory here, we used yesterday, we talked about monopole and charges, okay? Now, if you take this theory here, and this is not the only thing that you can do, you could add another term that is called the theta term, that is FF dual, and the effect of this theta term is to give charge to the monopoles, and you can play a game very similar to this game that I did, and you will see that you have a phase in which this object that is charge plus monopole condensate, and this will give rise to an oblique confinement phase that, as he was explaining yesterday, is what explain this pseudo-gap state in ITC superconductor. So, but I don't know about the contact with oxygen.
Turned it off. Oops.
Maybe I can just answer it. What she's trying to say is that if you just modify this a little bit by adding a topological term, this leads to the model of the pseudogap and high TC that I spoke yesterday briefly. So
but
it's
I
very
don't know
important.
if the oxygen, what is the...
Basically, this one layer thing is not going to be different in superconducting properties from the bulk material.
Yeah, it's
Yep.
3D, that's why, yes?
Yep,
Okay.
exactly. Thank you very much.
It's a pleasure.
And
Cristina,
don't go away. And now we like to invite the second speaker of the session, Javad Shabani, induced superconducting pairing in integer quantum Hall edge states.